Hello everyone, this is Dr. E, and for today we're going to be talking about limits, how to solve limits, how to understand the notation involving limits so that we'll be able to better understand the language of calculus. One of the many challenges of students taking calculus for the first time is that they're intimidated with the notations that they are seeing for the first time. And this is a common problem for most students who are trying to get into the groove of understanding calculus and to be able to overcome the anxiety and sometimes intimidation of the notation in calculus. That is what we're going to be working and talking about today when we start working on how to answer limit analytically and graphically. And special shout out to STEM Fam, our STEM warriors, who are a group of students who are aspiring to major in any STEM majors or STEM courses in college, and perhaps perform or do work in STEM in the future. So to be able to help them be less intimidated with the language of calculus, let's start with how to read and understand notation similar to this one. And these are some of the reason, as I've said, that is intimidating most students seeing big mathematical problems similar to this one that some or most students can't even read correctly. So in this particular notation, we read this as limit of 2x squared minus 5x minus 3 all over x minus 3 as x approaches 3. So it's still too much to digest, but once we start working on how to solve this limit graphically, it's actually really simple, and this notation is helping us to understand how to answer problems on calculus like what we're going to be doing in a little while. So to get yourself acquainted with some of the functions that you might see and solve in finding limit of a function, one of them would be the limit of the square root of x plus 4 minus 2 all over x as x approaches 0. So it's kind of like a tongue twister here, but once you get used to it, you'll be able to read it like limit over the absolute value of x plus 2 minus 2 all over the absolute value of x as x approaches 0, or the limit of this complex fractions like 1 over 2 plus 1 over x all over x plus 2 as x approaches negative 2. So these are some functions that you might encounter in calculus, and you'll be able to understand and answer this a lot easier and with confidence once you understand how it works graphically and how it works algebraically or analytically. So in calculus or in mathematics, functions or f of x can be represented in many forms. One of them would be the most familiar for most of you, which is writing out f of x in algebraic form. So we have here 2x cubed plus 3x minus 1, which is what we commonly see in our problems in basic algebra and intermediate algebra. We also have f of x in table form, like what we are seeing here right now. Notice that we're not seeing the equation anymore of this function, but we're seeing the table of values associated with this function. So if x is equal to negative 3, y is 0.23. If x is 0, y is 3.3. And this is an f of x in mathematics, but not in algebraic form, but in table form. And if we have an f of x in table form, we also have f of x in graph form. So these are the three common notations or three common forms of f of x that's given in a calculus problem. So sometimes f of x can be in algebraic form or in table form or sometimes in graph form. And all the questions that you will be asked will be sometimes in finding the derivative of f of x, finding the integral of f of x, or finding the limit of f of x given these forms. So let's start with the easy ones. So let's work with algebra problem like this one. If we're going to look for f of 2, f of negative 1, and f of 0, given that f of x is equal to 2x cubed plus 3x minus 1, this is going to be straightforward because all we need to do is to substitute the value of x, which is in this case 2, negative 1, and 0, to our f of x so that we can find the value of f of x, also known as the y in our function. So if x is equal to 2, y is equal to 21 because 2 times 2 cubed plus 3 times 2 minus 1, using the order of operation, it's equal to 21. And if x is equal to negative 1, use the substitution rule, and we'll have f of negative 1 is equal to negative 6. And if we have f of 0, by direct substitution, we'll have 2 or 0 plus 0 minus 1, which is equal to negative 1. So this particular problem is a problem on algebra. May not be in calculus, but you'll see this, or it can also be a calculus problem, but you can usually or often see this in an algebra problem. And it's easy because the notations, we are all familiar with f of 2, f of negative 1, and f of 0. But sometimes when we have notations that we don't understand, it becomes a little bit more challenging. So take a look at this example. So now we're seeing f of x not in algebraic form, but in graph form. So in this case, we're going to solve for f of negative 1, f of negative 3, f of negative 4, and f of negative 6. And to find these values, all we need to do is to look at the graph, and by observation, we'll be able to find the value of our y given x using f of x in graph form. So if x is equal to negative 1, we know that y is equal to 0. If x is equal to negative 3, we know that y is also equal to 0. If x is equal to negative 4, y is equal to positive 6. And if x is equal to negative 6, y is equal to 0. So it's pretty easy, straightforward, and it's impossible not to solve if you know your notations like this. But for students who are not familiar with the notation, let's say second grade students working out a simple problem like this in algebra, they're not going to answer this easily because they are not understanding these notations. But of course, you who are watching right now can understand this fully because you already know algebra prior to working with calculus problems. So that is why it's important for us to be able to know the language of mathematics, because if we know how to read them, solving them will be a lot easier. So let's have another type of f of x, in this case, a piecewise defined function. It's a piecewise defined function because we're seeing multiple types of graphs in one f of x. So we're seeing a parabolic graph, we're seeing a linear graph, and we're seeing a dot that is represented in an f of x, which is a constant. So let's find the value of f of 0, f of 1, and f of 2 by just looking at the graph, which is really easy because if we know where f of 0 is right here. So that means f of 0 is equal to 0. And f of 1, which is here, is equal to 6. Now notice that at x is equal to 1, we have three possible options that most students are also confused about. Is it going to be this dot, or this dot? Of course, it's going to be the dot that is shaded because we know that in algebra, an open circle is a symbol to denote that that particular function does not exist at x equal to 1. But since we have a dot right here, it exists because at x is equal to 1, y is equal to 6. And if x is equal to 2, zoom, y is also equal to 6. So now, let's take a look at problem number 4. We're seeing an unfamiliar notation for most of us because now we're seeing the limit of f of x as x approaches positive 2. How are we going to solve it? And how are we going to use our knowledge of calculus to be able to answer this particular problem? So before we undergo some calculus problem and answering this analytically or graphically, in this case, we need to know what it means by the limit of a function. So by definition, In mathematics, the limit of a function is a fundamental concept in calculus and analysis concerning the behavior of the function near a particular input. And in this case, our input is at x approaching 2. So what will be the value of y as x approaches 2? Let's solve this limit graphically. So we have many ways on how to solve limits in calculus. One is by looking at the graph or solving it graphically, and the other one is analytically or algebraically, which uses mathematical techniques to be able to solve problems like what we're seeing here. But since we are doing it graphically, it's actually a lot easier because all we need to know is how the notation works and how it translates to our f of x. So as x approaches 2, it means coming from the left, coming from the right, the function should meet at exactly the same height of the function in this particular graph. So let's check it out. So coming from the left, our function at x is equal to 2 is approaching, boom, it's approaching positive 4. Now let's see if it's also approaching y equals 4 from the other direction. And coming from the right, our y is approaching a different height in this particular piecewise defined function, and it's at 8. And when this happens, our limit does not exist because the behavior of the function from the left and from the right is approaching a different value of y. One is at y equal to 4 and y is at y equal to 6. And when that happens, our interpretation for that particular function will be that the limit at x approaching 2 does not exist. So this is how we use our visual to be able to understand limit of a function. So the limit of the function as it approaches x is equal to 2 does not exist in this particular notation because at that point, the function is not approaching the same height of our graph. Now let's try to use other limit of a function so that we'll better understand how to answer this graphically. So let's say we are looking for f of x as x approaching 0. So 0 is somewhere here. So from the left and from the right, let's see if it's approaching the same height. Coming from this direction, x is going at this point. From the other direction, x is also going to this point. So that means this limit exists at y equals 0. So that number or that function exists as x approaches 0 because it's approaching the same value of the graph or height of the graph coming from this direction and coming from the other direction. So that's how we answer limit of a function visually or graphically. And if we can answer it graphically and visually, answering it algebraically or analytically will be a little bit easier this time because now you're visualizing why sometimes our function does not exist. So let's have the next example. F of x as x approaches -1. -1 is somewhere here and coming from this side of the equation and this side of the function, it does exist because it's approaching the same value of y, which is equal to 4. So for number 6, f of x as x approaches -1 is equal to 4. And for f of x as x approaches 7, if we're going to use our scale, this is -1, this is 0, this is 1, this is 2. So we need to extend our x-axis so that we can represent 7, which is somewhere here. And when we look at our function from the left side and function from the right side, we notice that there's no function that's existing at x equal to 7 because for this piecewise defined function, it's only true within this range of values. So that means our problem for f of x as x approaches 7 does not exist because the function does not exist in that particular value of x in the first place. So these are some of the many forms or reasons why sometimes our function does not exist in a limit. So let's have more problems involving limit of a function, but this time with different notations. Notice that on problem 9, 10, and 11, we're seeing positive and negative sign on top of our value of x. So does that mean that it's a negative 2 or a positive 2 or a negative integer? The answer is no, because these symbols or notations are what we call as the direction of the limit that we are looking for. So in this particular case, for problem number 9, limit of f of x as x approaches 2 from the negative side or from the left, we are just concerned or interested as to where that function is going, coming from this side of the equation. So we're only concerned on one side of the function, which is in this case, the negative side. So coming from this side, our value of f of x as x approaches 2 from the left is going to be 4, and it exists because we're only concerned about one side of the limit. So for number 9, with this notation, it exists because it exists at 4. And for f of x, as x approaches 2 from the positive side or from the right. Did I say from the right a while ago? So forgive me if I am confused with my words, but you know what I mean. If this is a positive sign, it's coming from the positive side of the function, which is from the right. So in this case, our y value is going to be at 8. So it also exists because we're only concerned at one side of the function. And for problem number 11, at x approaching 0 from the right, or positive value of x, we know that it exists at 0 because coming from here, it's still going to this particular value of y. So why are we doing or working or understanding this particular or answering this particular problem? Because this is another type of function in calculus that we should be aware of, and we call this a one-sided limit because we're only concerned on this particular side of the limit, and in this case, 2 from the left or the negative side, and this is what we call in calculus as one-sided limit. So this is another way on how to look at solving functions or limit of a function graphically using one-sided or a regular limit problem according to the notations that we are working on. So if we are seeing function like this, solving for a limit of 2x plus 3 as x approaches 2, 2x cubed plus 3 as x approaches 2, 2x plus 3 as all over x minus 2 as x approaches 2. How are we going to solve them if we are not given a graph? Well, that's going to be a challenge because, as I've mentioned, it's always challenging to answer math problems, specifically calculus problem, if we are not seeing the graph or the graph of the function is not available to us and we need to still solve for the limit. So how are we going to do this? By direct substitution. And direct substitution is just one of the many techniques that we can use in solving limits algebraically or analytically, or basically solving limits if we don't know or see the graph. So how are we going to solve problem number 1? All we need to do is to substitute. So if we have limit of 2x plus 3 as x approaches 2, all you need to do is to substitute your x with 2. And we have 4 plus 3, so this limit exists at 7. So this one, it exists at equal to 7. And for problem number 2, same thing that what we did for problem number 1, limit of 2x squared plus 3 as x approaching 2. So by substitution, 2 squared plus 3, 2 times 4 plus 3, 8 plus 3, and my pen is dying, and we have 11. So that means our limit exists using the substitution method at x equal to 11. And for problem number 3, I'm not going to use my other pen, but this one right here, limit of 2x plus 3 as x approaching, or x minus 2 as x approaches positive 2. So by substitution, 2 times 2 plus 3 all over 2 minus 2. We have 4 plus 3 all over 0. We have 7 all over 0. And we know that if we have a fraction and the denominator is equal to 0, that means that this fraction is undefined. Or in calculus, this basically tell us, even if we're not seeing the graph, that this function as x approaching 2 is DNE or does not exist because our denominator turned into 0. Now, how are we going to make sense or visualize what is happening here when a rational function like this turn out to be a fraction that is undefined? So we're going to be using our technology, and in this case, Desmos. So Desmos is a graphing tool that we use to verify the graph of the function. So this is the graph of problem number 3. And if you don't know how to use it, it's pretty simple. You just need to use your keyboard, and 2x plus 3 is right here. Type it in, divided by x minus 2, and you are seeing now the function of our graph, or the graph of our function right here. And this is now our f of x using a graph. And if we're going to zoom it in, we are seeing that at x is equal to 2, it is your asymptote, and that is why we know that that x value does not exist in this particular example. So this is why technology is our friend in calculus, because we are now in 2022. So this time we have many apps that we can use, so that whenever we're solving for calculus problem analytically, we have a way on how to verify if our answer is correct, even if we don't have the book or the even numbered problems in our textbook, which is usually not provided in, or those answers are not provided in the textbook. You can use Desmos to graph it, so that you can verify if your answer is correct. The operative word is verify if your answer is correct, and not cheating, because you don't cheat, you're just verifying if your answer is correct. And this is true because in this particular case, if we find the graph of this function, that's just like what we showed you. This is the graph of the function, and this is at x is equal to 2, and we have the asymptote here at x is equal to 2. That's why it does not exist. However, is this always the case? Is this always how easy solving for limit analytically by substitution? The answer is no. Why? Because take a look at this example. If we have 2x squared plus x minus 3 all over x minus 1 as x approaches 1, by direct substitution, we see that it does not exist because the denominator will turn to 0. However, we also know that 2x squared plus x minus 3 is a factorable quadratic equation, because we know algebra and we have mastered our factoring techniques. So if we're going to modify 2x squared plus x minus 3 by factoring, we can modify it into x minus 1 times 2x plus 3. And now we can cancel out the x minus 1. And now we know that that limit actually exists, because if we use x approaching 1 to substitute to 2x plus 3, which is what is left with our function, it will be 2 times 1 plus 3 equal to 5. So that limit does exist at y equal to 5, because we're able to use factoring to be able to verify if this is correct. And this is how we answer problems in calculus analytically. So problem number 1, 2, and 3, we are given a complex fraction. That limit exists if we can only simplify our complex fraction and then substitute the value of x afterwards. Even though by substitution, we know that this does not exist because the denominator will automatically turn into 0. Same with problem number 2, irrational functions with radical. By substitution, it may seem that it does not exist, but if we rationalize this using algebra, this limit will exist. And if problem number 3, by substitution, the denominator will turn into 0, but if we use our factoring technique, the factor of x squared minus 3x, or this particular problem can be factored out, and it will exist eventually, and we'll be able to answer and solve this limit analytically. And this is how we answer problems in limit of a function. More examples on how to find the limit of a function analytically in my website or in my YouTube channel. So just go to my YouTube channel and type in or find some videos of how to solve limit analytically, and we'll have more problems that focusing on that particular example, because now I am confident that most of you are understanding the language of calculus, specifically in limit of a function, because as I've mentioned, the whole idea of this lecture is for you to understand that calculus is difficult if you are not understanding the notations associated with the problems that you're working on in any calculus problem. So the key here is, of course, understanding the notation first, understanding how the function works graphically, so that when you work on problems using different techniques in algebra, in calculus, you'll be able to appreciate your work better. This is Dr. E, and see you again next time. So to our STEM warriors, I am all with you in your journey towards achieving your goal of earning a degree or even a career on STEM.